Hello, this is MATH1131 Calculus, and we're having a look at a few sample questions out of the Calculus problem booklet. So this one's from Chapter 3, question 10a, and it gives us, it says we want to find a function or find an example of a function which is continuous everywhere, so you can draw it without taking your pen off, continuous on R, and it's got to go to 0 as x goes to plus or minus infinity, so it's got to taper off both ends. And we want to try and cook up an example that has a maximum and a minimum. So to do this, one simple way of doing it is just to give an example by drawing the graph and not actually being so explicit and writing down a formal equation for it, although I'll do that as well. But to just draw a picture to try and illustrate a function that may have this property. So it has to go to 0 as we go off to infinity or minus infinity, and it's got to be continuous, it's got to have a max and a min. So I might sort of think of some kind of function like this that zips off to 0. That way it's got to have a minimum. I want to have a maximum, so I want it to turn and do something like that. So I could just draw a picture and say, look, there's an example of a function. It clearly tapers off to 0 at both directions as I go to plus or minus infinity. It clearly has a maximum there, local maximum, and it clearly has a minimum. In fact, it'll be a local and global minimums and maximum. You could write down a formula for this if you've drawn enough curves. You might look at this and say, well, a possible equation for this might be something like x e to the minus x squared. Now that's hard. If you don't see where that comes from, it's only coming because having drawn lots of curves, having drawn this function many times, I just remembered that was the basic shape of it. And you can check that it has all these properties. You can see that as x goes to infinity, this term is going to dominate. This is going to go to 0 more quickly than that goes to infinity, and it'll be the same plus or minus infinity. So this clearly goes to 0 as x goes to plus or minus infinity. And if you look at if you find the derivative of this, if I work out the derivative of this, I will get minus 2x squared e to the minus x squared plus e to the minus x squared. And this will be 0 when minus 2x squared is equal to 1. So that's when x is equal to plus or minus 1 on root 2. And so this will correspond here. If you put plus 1 on root 2 in, you'll get some positive height there. And if you take minus 1 on root 2, you'll get the other value there. So again, if you were asked this in an exam or test, a picture would suffice just to draw a diagram. You don't necessarily have to produce the formula for it, but it can be done. For part B, you are asked also for a function that goes to 0 as you go to plus or minus infinity, but you want it to have a minimum value but no max. So it's got to have a minimum but no maximum. And once again, a picture would suffice. So if I draw up a picture trying to demonstrate such a function, you want it to have a minimum but no maximum. It's got to go to 0 both ends. So probably I'd just draw something like this would suffice. And so there's a minimum, goes to 0 both ends. It's got no maximum because it gets arbitrarily close to the x-axis, but it never gets there. So the function is always less than 0, but never actually gets there. So f of x, this f of x I've drawn here is less than 0, but f of x is never 0 in my picture. And again, you could cook up an example of such a function. If you think about it for a little bit, again, depending on how experienced you are and what functions you've played with. So if I take the function f of x equals to, what would I do here? Well, if I take e to the minus x squared, e to the minus x squared does this, and I wanted to reflect it in the x-axis, so I'll just put a minus there. So that would have the property, this function would have the property, it's got a minimum here at 0, and a minimum value there of minus 1 at x is 0, but it's got no maximum because it's getting as close as you like to 0, but never gets there. And you can see from that equation that that would be true there. So there's just a couple of examples of functions that satisfy the requirements.